Okay, good afternoon. Can you hear me?
Yes, hello.
Yes.
Yes, we hear you.
Okay. Can you see the slide?
Yes.
Today we will continue and try to finish the sand management. Sorry. Yesterday we started talking about the gravel pack, open hole gravel pack and internal gravel pack, the specifics of each other and the performance of each other, external and internal gravel pack. What are the main considerations for the open hole gravel pack and the internal gravel pack? We also talked about the frac pack, which is a sort of internal gravel pack, but this is a perforation with the creation relatively small fractures to increase the effective wellbore diameter or inflow area of the well, hence increasing the productivity of the well. And the comparison between the frac pack and gravel pack, when the frac pack provides more more productivity with while having less skin effect on the well performance. We have looked at the ACG Chirac sand control completions skin comparison as well, establishing that the as we said before, the with the cased and perfed well with wells with no sand control would have less skins, whereas the open hole gravel pack are ones almost with the highest skins, and the standalone screens, including the expandable sand screens, are the somewhere middle, having low skins, but the performance of the wells are equivalent to the cased and hole wells, and those are providing more or less good sand control as well, until the water breaks through, which we will talk about a little bit later. Then we talked about the parameters or factors that affect the gravel pack performance, gravel pack efficiency. One of these is the gravel pack sand size or gravel size, which in case if it is too large, then we may not have any sand control effect, or if it is too small, then we don't have then we compromise, or we get reduced well performance, or in other words, we wire the reducing the permeability of the gravel pack and the bridging around the plugging the gravel pack, hence the productivity of the well will be reduced as well. Then we learned what is the uniformity coefficient. So the size of 40%, the ratio of the size of 40% of the sieve analysis distribution over the size of 90% sieve analysis distribution, and here is the uniformity coefficient equivalence. So graphically or visually, if you see that one PDF curve, this is called CDF curve, cumulative distribution for curve function, or cumulative. This is a histogram or the distribution, and this is the cumulative distribution when this distribution is normalized to the total numbers, and the last number should be equal to 100% because this is cumulative distribution. So if you see the steeper CDF curve, cumulative distribution function, then that means the ones that is steeper, that has a less C coefficient or uniformity coefficient, and this one, here the sand number 1 is more uniform because it has uniformity coefficient equal to, as opposed to the sand 2, which has a uniformity coefficient of 8, and that's clear from these graphs and this graph. When we have D40 for this, for the dashed line or sand 2 is far away from D90, and the size of this D40 is much larger than D90, and the so D40 40% of sand size is much larger than 90% sand size. Here, the difference between the D40 and D90 is much lower, so uniformity is less. So it's well sorted. It means the sand grains in this example, in this sand, are close to each other by the sizes, so there is not much range between the sand grain size. Then we learned the social criteria and Schwarz criteria. This is the explanation or the graphical presentation of Saucer experiment when he flow the fluid through the bracket, which has a formation sand and the gravel pack sand, and then by changing the grain size of the gravel sand and the formation sand, and at different ratios of average diameters of the reservoir and gravel sand, it was established that the best ideal gravel sand must be is laying for the this ratio value, which is the D50 of gravel sand over D50 of formation sand, is between 3 and 6 when the best sand control or sand prevention is achieved, as well as the permeability from flowing from this formation sand through the gravel pack sand is maintained as initial permeability, so permeability is not damaged. In the cases when this ratio is too small, up to 2 or 3, then well productivity reduced because the gravel packed sand is too small and the formation sand would the permeability of gravel sand is less than formation sand permeability, and in if we get larger than 6 between 6 and 17, then the this is assuming that this line is equivalent to the formation sand permeability, and then the gravel pack sand size gravel the grain sizes are large enough to some extent prevent the sand production, but the sand will invade into the gravel and start plugging it, and then the permeability of the system will go down. Even it may go down below the formation sand permeability. And then if it is larger than 17, this ratio, then the permeability of the system is not reduced, but on the other hand, the gravel pack sand grain size are too large to prevent any sand production. So all the sand in the formation will be migrating sand from the formation will be produced to the wellbore. So no sand control will be achieved. So that's the social criteria. It says a D50 over this ratio should be between 3 and 6. There's another criteria which is developed by the other engineer called Schwarz. This is almost similar kind of results, but here it's a little bit more detailed graduation when the Schwarz considering D10, D40, and D70 for the different uniformity sands. Okay. The next factor that is affecting the, especially it is important for the internal gravel pack or cased and perforated completion gravel pack is the perforation diameter. As we said before a few times, that for the gravel pack or hydraulic fracturing, when we want to inject some propants into the well, we must have a larger entry diameter perforations. So to prevent the sanding out or screening out the perforations in the tubing or in the perforation tunnel entrance. So the perforation tunnel can be filled by the gravel pack sand fully, because otherwise it would be inefficient gravel pack in the perforation tunnel and inefficient sand control, as well as the since the formation sand will invade the gravel pack, not only sand but the shale fines also can invade the gravel pack, then it will be also a well performance compromised, meaning reduced productivity, reduced permeability through the perforation tunnel, which will lead to the reduced productivity. Okay, here you can see different entry holes and the so cross-sectional areas of the perforations, and here we have a field with the 0.5 Darcy formation sand, and here we have a different increasing size of entry holes and perforation field with 180 Darcy gravel. So the and this is the pressure drop across the perforation. So this is showing the perforation filled by the formation sand. So it will increase the pressure at even very low rates. That means the permeability of this system, of this perforation, will be very low. But if we as we increase the perforation diameter, entry hole diameter, the perforations filled with 180 Darcy will get less pressure losses at even higher flow rates per perforations, and that's 100 barrels per day per perforation, which is very good value pressure drop through the perforations. So that's clearly showing it's a kind of calculated type data, but it is clearly show that the larger the perforation diameter, the better, and the perforation must be fully filled with the gravel, and the gravel permeability is quite high, and that is providing a very good productivity through these perforations. The larger diameter, the better the fillage, then we can get very low pressure drop at even quite high rates through the individual perforation. Okay, so another factor is gravel packing fluid. So the fluid that we inject this gravel into the well bore through the system, and then the so this fluid usually 1% potassium chloride brine based fluid in most cases. Sometimes we add polymers if there is a need for increased viscosity. So to make sure that the gravel is delivered further and slower, and so these are the functions: control formation pressure, so similar to drilling fluid. So the ppg, or the density of this fluid should be equivalent or above the formation pressure, so there is no blowout. Transport gravel to completion interval. So you will this table is in your book. You can read out this and remember. Okay, this is important parameters. These are kind of the practical examples comparing the brine pack and the gravel pack with the performed with the viscous gel fluid. So it's showing the importance of transport fluid. So as you can see in the example in the well that is on the left hand side, we have a brine packed. So the brine fluid used for the gravel pack, for the packing, and we achieved very good gravel pack here, and this the logs are showing very good gravel pack. So at very high depths, well, very long depths, let's say, and almost the same depths, a little bit deeper, and they used viscous gel pack in oil well, and you can see the some areas that the empty or not filled with the gravel fully, and it is again shown on the neutron gamma caratage, gamma ray logs, the neutron logs, and the gravel pack imaging logs. That this one is not filled fully. On these examples, this wall is gas wall, and the gas wall is also they used viscous gel pack, and we have this kind of empty zones within the wellbore, and then they used a brine pack in the same well to recomplete the packing in the same zones, and you can see the packing was done fully up to the casing or liner shoe, and this gravel pack is much more complete and perfect than this one. So this is the same wells. Initially they started with the viscous gel, and then completed it with the brine gel to fill it. Okay, so here's some recommendations were done that based on the results of laboratory testing and field experience. Under a wide variety of well conditions, brine provides more complete packing of the perforations and annulus, and it should be considered as a general purpose gravel pack fluid. Gel added fluids or more viscous fluids should be limited to use in the wells with deviation less than 45 degrees or close to the vertical wells, and gross zones length that is less than 70 feet. So for the long intervals to be completed, the gel pack does not perform as good as well as the brine, and it can be understood because the viscose fluid for the long intervals may just get very viscous, and they will move without filling this because of the high viscosity. Okay. This is the surface equipment infrastructure for the gravel packing. So we have a filter units for 10 microns and 2 microns sands, and then it goes through the polymer adding. This is filtered fluid, and sorry, not sand. It is filtered to get clean fluid, and then it goes through the paddle mixers to mix the polymers as required, depending on the conditions of the well, and we get viscous or non-viscous fluid with the base potassium chloride brine, and then it is pumped through the gravel, and gravel, the slurry is pumped with the high pressure pump into the wellbore. The further pass, it goes through the tubing and through this crossover crossover is down here, and it goes through the tubing, and at the crossover it turns to the annulus and starts filling the annulus between the formation and the screen, and then the almost half of the fluid goes to the gravel is depositing or accumulating on the in the annulus, and the fluid is leaking to the formation, and half of it going back to this wash pipe to the surface, and again recirculating back into the well with new portion of the gravel. As it is filling up up to this liner top or to the shoe, then the pressure starts increasing, because now the whole annulus is filled by the gravel. As this pressure starts increasing, and this pressure is monitored on the surface at the pump station, and then this the crossover is pulled out to close this pass, and the gravel pack fluid, the rest of the fluid with gravel or without, is circulated back until it gets cleaned from the gravel. The wall bore is cleaned from the gravel, until the clean water is received at the surface. So that's kind of briefly how the gravel pack operations are done. So again, it is going through the fluid is processed through the filters up to the 2 micron for the 2 micron up to the 2 micron solids, and then filtered fluid goes through this paddle mixer with the polymers to get viscose or non-viscose or some additives to get some specifications to deliver the gravel in different conditions, and then it is pumped into the gravel paddle, and this gravel is mixed with this fluid and goes through this high pressure pump, and high pressure pump injects this slurry of the fluid and the gravel into the well bore, and it goes through the tubing, through this crossover, filling up the annulus between the screen and the formation. This is the under limit area of the formation, so it fills the this area up to the casing shoe, and then the increased pressure at the surface at the wellhead is dictating that, well, indicating that the gravel is filled up, and then this crossover is pulled over this packer, and the the fluid is circulated to the surface until the clean water or clean brine are received at the wellhead. That's the end of these operations. In more advanced ways that I've seen in Chirag wells and the Azeri wells, they have a shunt tubes. These shunt tubes are helping to, so through this we have in this technique, I will show next time these gravel packing operations with shunt tubes, when they have some kind of tubes like this. So it goes through this, and to provide better feeling, not to not leave any space. So shunt tubes actually are not here; they are here. So the fluid goes from the wash pipe into the annulus area, and these shunt tubes are helping to fill each zone individually. Okay, so there is no gap left between these in this annulus. So this is a little bit advanced. This is a very schematic view, and there are some that what I'm trying to point out, that there are some advanced ways of gravel pack operations, but the main thing that you understand how it happens, it goes through the tubing and go to the crossover tool, filling these annulus with the sand between the formation and the screen, and then the fluid is circulated back to bring new portion of the gravel sand, and the some portion of fluid, of course, will leak to the formation, and then hopefully produced back to clean the damaged zone. But anyway, this is the operations, how it's done. After we complete this the gravel pack operations, we have to test or check how we have done with the gravel packing. So do we have complete gravel pack along the screen, or do we have a leftover zones? So there are a few nuclear density logs which shows through the density of the gravel sand and the empty zones. We can identify where the empty zones are. Compensated neuron and gamma ray logs also can show the, you can see here, it's the same well, and this showing that this gravel pack, here is the top of the gravel, and then they topped up with the brine again up to this level, so the gravel is up to this above the screen top, and just below the liner shoe. So this is a kind of measurement with the, and this is the gravel pack evaluation. This is calculated value from this gamma ray and CN, compensated neutron log. There is a tool called distributed acoustic sensing, which allows through the sonic acoustic logs, it can be tested, can be logged or measured the sanding areas or the efficiency of this gravel pack. This tool is also used and tested in ACG walls as well. Distributed acoustic sensing tool systems, and this is also helping to understand how efficiently the gravel pack is performing, or any sand control vessels are performing. And there is another way of pipe conveyed memory tools when we have a pipe or tubing or the liner with some radioactive pips on that pipe, and these radioactive pips are when we run the logs, we can see this helps us to identify empty zones as well, in the gravel pack if there is any empty zones. So the pipe conveyed memory tool is also a type of tool to evaluate the gravel pack fillage and performance, how it is it was performed, does it work well or not. Okay, the advantages and disadvantages of this gravel packing: again, effective over long intervals, 100-meter operation is possible over 100 meters. There are some disadvantages like mechanical restrictions in the wellbore, workover difficult, requires removal, fishing of packers, screens, etc. It's expensive for multiple intervals. So these are also in your book, so you can read it out and remember for your benefit, for your favor. Okay, the last thing I'd like to talk about from the sand management point of view is some kind of a ACG sand control development. In early times, the first 4 wells in ACG were drilled and completed as cased and perforated. And at that time, the SOCAR with very proactive position of especially Khoshbakht Yusufzadeh were insisting that, and they were producing at very high rates, up to 15,000–20,000 barrels per day. Okay, and at that time, the tubing was 4.5, 5.5 inch tubings. Later, for higher productivity wells, BP started, especially in Azeri, using 7-inch tubings. So the cased and perforated wells, as they started to produce at high rates, they started to produce very high sand production. And that was almost from the start of the production, without even without any water in the product. Yes, there were very low skins. The productivity was high, but that might be also because of the fact that the sand around the wellbore was produced and the effective wellbore was increased, and we achieved a point where the we had to limit our production to limit the sand production, to limit our oil production, to prevent the massive sand production, because sand would fill out the separators, all the vessels very quickly, and almost in 2 months' time we would have to to shut a separator and or full the facility to clean out this sand, and even sometimes just a working in confined space, shoveling out this sand from these separators. So when they moved to the standalone screens, and standalone screens are started with the slotted liners, then they went to the different types of screens, and then finally the most advanced standalone screens of expandable screens completions are sorry applied, installed in the wells to prevent sand. For the standalone screens, the slotted liners or wire-wrapped screens, sanding was dropped, was reduced, but that happened unless up to the point when the water started to break through the wells. So as we started to produce water, then this brought another massive sand production into the wellbore and to the surface. And expandable screen completions also were successful until the water breaks through, and their screen deformation was an issue because of high rates, high stress through this high drawdowns was kind of a questioned the performance of these expandable screens completions. And finally, the open-hole gravel packs were installed, were applied, and it showed very high efficiency in terms of sand production. And the completion team in ACG has also they wouldn't only work on the changing or testing different types of sand exclusion methods, but also with the open-hole gravel pack, there were some studies or the experimenting with the different drilling and completion fluids to make sure that the low damage achieved, so the low skin values are achieved, and also the completion itself or gravel pack fluids are also were developed to make sure that the sand prevention are effective as well. So, and at this point, the open-hole gravel packs are best kind of option used in the ACG. Why I brought this ACG example on, because this is very good example of testing, not testing, but kind of comparison of the different types of sand control methods, sand control technologies in unconsolidated sand reservoirs, where the sand production is inevitable, and especially with the water production, water breakthrough coming up. And the evolution of the sand control methods in Chirac and ACG show that the open-hole gravel pack is one of the best for now, although it requires, as we saw before in previous slides, it has many installation issues. It may have high skins, etc., etc. But this one is especially for long intervals, for good reservoirs, for high rates, these open-hole gravel packs are working best. Of course, you have to make sure that high pack efficiency provided. Again, as I mentioned, they used these shunt tubes to provide the high pack efficiency. I will try to find this. So, and through this high pack efficiency, high level of sand control were achieved. Okay. So this is all for the sand management. We've gone through the different types of sand management tools, sand control tools. Sand management and sand control tools. We've learned that sand management is the type of managing sand, letting the sand is produced to the surface to be handled at the surface, but this option is available only in specific cases when the when the rates are low, velocities are low, and the sand production can be handled. It must be monitored through the wellbore, through the wellhead, at any bends or any valves, so we can monitor the conditions of the tubing. So it is under control. Only in this case we can talk about the living with sand option or sand management, and we have to first realize or define what is the sand-free rates for this kind of operations of the wells. And the other approach is obviously prevention of sand entering the wellbore, because if the sand enters the wellbore, it will reduce the productivity, it will reduce the flexibility of the well to be for the interventions, and therefore we want to prevent or exclude any sand entering the wellbore. So for that we have a mechanical preventions, again using the as we said here, the different completion types that will reduce the drawdown through the reducing the drawdown, so the drainage area is increased. So the flow geometry. So the flow geometry is that to prevent sand mobilized to be mobilized in the reservoir and flowing into the wellbore, or controlling rate again to not to allow high stress on the wellbore, changing the drawdowns slowly, and achieving the better sand-free rates. Okay. Any questions? Hello?
Yes, teacher.
Any questions? Tomorrow I will talk about some introductory elements of hydraulic fracturing. This is very important subject, which is not in your books, so please be attentive. So you may have questions on this subject as well, topic as well. Of course, it will be introductory, some very basic elements, and probably some elements of MPV or project economics, which I promised to provide earlier to help you with your FTP project as well. Okay. Next week we will review what we covered through the semester. We will have, beside that, we will have 2 consultation hours before the exam. And your exam, I think, is on the 1st of the February. Okay. Hello?
Clear. Okay, teacher. Okay.
Good. Then, if you don't have a question, have a good time, have a good day. We are going to have a FTP sessions with the group 1 and group 2 at 3 and 4 respectively. So I'll see you at 3 o'clock. Is that okay? Aytaç Hanım and Türkan Hanım.
Yes, sure, madam.
Okay. Türkan Hanım, one request. Can you be kind of your team actually alert in terms of if we finish with the first team earlier, so we can start as soon as we finish with the first team.
Okay, just inform me about that, and I'll inform the group
Okay.
mates as well.
Okay.
Okay.
Thank you very much. See you